And I want somebody to mishear me and say, did you say sequins? Like on a dress? No. Okay, that was unbelievably non-optimistic, I think. Somebody give me an example of a sequence. Okay, numbers. Yes. Pattern, okay. Somebody give me an example of a sequence.
1, 1/2, 1/3, 1/4.
All right, so 1, 1/2, 1/3, 1/4. Can somebody tell me what the nth term would be? So I'm going to say this is the first term. So everybody, isn't that crazy of me to say? That's the first term. We're actually going to call that A1. So you're not going to believe this. What would that be?
A2.
Holy shit. So what would AN be? 1 over n. Okay, so we have an idea of a sequence of numbers, and I love it. You guys got it exactly right. There must be some kind of a pattern. The pattern itself could change, but it has to change in a regulated way. So let me give you an example. This is very straightforward. Is that cool? Start with 1 and divide by whatever place you're at. So 1 divided by 1, 1 divided by, I'm in the second place, 1 divided by 2, blah, blah, blah. Obviously, the most simple sequence would be 1, 2, 3, 4, 5. Woo! What about this sequence here? Now, every time I say that, all I can hear is sequence. That's good, Jeff. What about... What's that sequence? It's trying to be a 9, by the way. Yeah, just keep subtracting 3. Now, this sequence is a little bit... Are you going to... Okay. I'm going to do the age-old tradition. If it's not doing what it's supposed to, turn the damn thing off. Oh, it won't even turn off. Which one's your power? Is this your power? Yes. 6, 7, 8, 9, 10. Okay. That's right. If you don't work, you don't get any power, damn it. All right, let's see. Okay. I miss my chalkboards.
It's because you didn't like shake it or hit it against the table. That's what I do with the TV remote.
Oh.
You take the batteries out and you like shake it.
Understood. I'll never forget, I had this old cathode ray tube TV, and it stopped working. So I took it apart, I blew dust around, and I put it back together, and it worked. And I was like, I'm a TV repairman, who knows? So when in doubt, blow the dust around. So what I want you guys to do, just take a moment. Can anyone figure out, don't say anything, what the nth term would be? And just to help you, it is not n minus 3. It's not good enough. That's obviously not good enough. That would be the increasing functions. Oh, it can't be right. Can you figure? Yes. Sorry. Don't say anything. Sorry, Macy. Just hold it. I'll ask for who got it. You want to show them? You got it written down? No. Okay. If you write it down, I can tell you if it looks good. Just want everybody to try it out. Don't say anything about it. Sorry. Just I love you guys. Can everybody try it out? Some of you guys are doing all the work in the head, which is neat. Yes? Oh, you're trying to whisper. Hmm? Where is it? Let's go. So I want to know. So I want to know what he said that is first. I want the function for the relevance to tell me what the other actions. Yes, good. So what I want, what did I do up here? Was an a function of n up here? And if I plug 13 into it, what do I find? 1 over 13, and what does that represent? The 13th term. I want something similar here. If I plug 13 into the answer you get, into the function, it better give me what the 13th element would be in the sequence. Huh? No. No. What's happening? What's this? 0 plus 7? Test it. So like, if you plug a 3 in, you get 36. Test it. Ooh, did you test it? Plug a 3 in, see if you get 36. Right, because you already know what the third element is. Okay, cool. All right, we're all circling the idea. Be careful, you should check it. Try to plug a 3 in and see if you get 36. All right, anybody else that he didn't get to thinks they got it? So here, watch this. Let's build it. A1 is 42, yes? Now, the overriding idea here is subtract 3. So you wish you could just say, AN is subtract 3 enough until you know, but you need a mathematical formula that it can plug a value in for it. It can't be a verbal description.
A sub n minus 1.
Sorry? No. Well, sort of. 3's, we'll see. A2, how do I get to A2 from A1? Minus 3, yes? How do I get to A3 from A1? So minus 2 3's. This is minus 1 3, and this is minus 0 3's, yes? All right, now real quick, I need you to understand something. You're going to be doing exactly this. Not a ton, but enough. So everybody kind of with me? Do you see what I'm doing? I'm trying to tease out, because what's the whole idea here? There must be a part of the way to get to the next term that is controlled by where I am. So if I could just write, where do I start? How do I get to the next two? And then I can tease out what is changing. What is changing? Yes? Let me stop for a minute. Do you guys see that? This is one reason why a lot of students don't like this as much as I wish they did, because that is not quite related to anything you've done before directly. You sort of do this with word problems sometimes, but nowadays there's not a ton of word problems in a lot of curriculum. We don't even teach algebra here because, who needs it? Algebra, what the hell? Just in case you didn't pick up, there's a lot of sarcasm. So on the first, to get to the first thing, I take away 0 3's. To get to the second, I take away 1 3. To get to the third, I take away 2 3's. So to get to the nth, I take away n minus 1 3's. Do you guys see that? Does everybody see that? Now, real quick, here's the funny thing. We're going to go by the textbook. What I mean is we're going to do it the way the textbook does it. Does anyone notice if we would have called the first term A0?
Yes.
This would have been better, because then it would have been n steps to get to this. In this case, if I call the first thing A1, it takes n minus 1 steps, and it's not as clean as it could have been. But is it difficult? No, it's just different from what you're used to. Yes? Do you guys see the utility in this kind of thing? If I said, okay, we need the 87th term, do you want to write the freaking sequence out until you get to the 87th term? Or you just want to stick a freaking 87 in this shit? Now, real quick, what should I do with this? I mean, this kind of shows the idea, but let's clean it up, yes? It'd be 42 minus 3n plus 3, so it'd be 45 minus 3n. Is that cool? And then I can check it. If I plug a 3 in, 45 minus 3 times 3, 45 minus 9 is 36. Check. You can always check your answer. Since you already know a few terms, you can just check it. Okay, how are we doing so far? Okay. Now, there are sequences that are almost impossible. And in fact, let me just expand that. There are sequences that are as close to impossible to find the relationship by hand as possible, right? I like that. As close to impossible as possible. So I'm obviously not going to give you a problem like that and expect you to do it. There'll be more like this. Obviously, they're going to get a little more complicated. Let me do another one here. Let me see. Let me show you an example of one that's a little bit more trippy. You could do it, Jeff. Dot, dot, dot. This one would be very difficult to write a single line equation because does anyone see the pattern? And when I say the pattern, it could consist of a pattern of a few patterns. 2 to 6, 7 to 21, 22 to 66. What do I do with those?
Times 3.
I multiply by 3. But 6 to 7, 21 to 22, yes? What would the next term be? 67. I did not. Last semester I was like, shut up. Is everybody with me? So it looks like if I'm on an odd term, I multiply by 3 to get to the next one. If I'm on an even term, I add 1 to get to the next one. You guys see that? Second term, I add 1. Fourth term, I add 1. Yes? This one's a little bit trippier. It would be, well, this might be an evil one to do this with because it kind of builds off the previous term, so it's also recursive, so it's neat. So we'll come back to that one. Here's the most famous recursive sequence. And you're all like, famous to who, Jeff? And I know you all know this sequence to some degree. Let me just write it down. Don't say anything. Now, does anyone know this sequence? All those you know. But yes, it's Fibonacci, right? So it's kind of silly, yes? Oh, no, I love it. So the arithmetic is based on addition subtraction. So like the 42 one would have been arithmetic sequence. Geometric sequences are based on multiplication. So like the 2, 6, if I would have made 18, 54, that would be multiplied by 3, that would be geometric. And we'll get to those in a minute. This is not either one of those. You can say it's some kind of a weird recursive arithmetic, but no, we don't call it. So you know it's Fibonacci. Has anyone ever heard of Fibonacci sequence? Has anyone never heard of it? Like, I don't know what the shit you're talking about. Is it a prereq that I know this shit? I did not read no Da Vinci Code, Jeff. Say again? Oh yeah, well, yes. The spiral? Yes. But so what? People don't always look at my shirts. Anyone that has never seen it before, be honest. Can you tease out what the shit the sequence is? What's the pattern? If you've never seen this before, can you see what the pattern is? It's very different from anything we've seen so far today. What you got?
So like the 2, you add the previous 2 terms.
Kick ass. So 1 plus 1 is 2. 1 plus 2 is 3. So forth. And the shirt that I wore is a rectangle that is cut in exactly the right place. And then you look at this rectangle and you cut it in exactly the right place. And then look at this rectangle and you cut it in exactly the right place. And then you connect all the corners and you get the spiral. We're not gonna suddenly become Fibonacci. You could take a year to study Fibonacci sequence by itself because you don't even know. Anyone ever heard of the golden ratio?
Just the two.
So, sorry?
Just the thing, but I don't know.
If you go far enough in this sequence, you could do it, Jeff. Can you? I used to know, what is this, 144? Blah, 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 blah. I think it's right. One thing that's interesting, if you want to know something, when I went to Canada, I was using Fibonacci sequence to really quickly convert kilometers to miles. And here's why. Can somebody have a calculator? What is 55 divided by 34? Keep going. 1.6.
17647059.
All right. And then what is 144 divided by 89? Sorry, dude, you've been chosen.
Same thing. 1.6179. Oh,
7, 7?
Yeah.
Okay,
7,
I thought I would have gotten to 168 by then. Now, if I keep going, it's going to approach a specific number. So it doesn't grow forever. In fact, 2 divided by 1 is 2. 3 divided by 2 is 1.5. 5 divided by 3 is 1.67. And then it kind of oscillates around 1.618, roughly. We call that the golden ratio. All right, again, I told you, we're not going to talk about Fibonacci sequence all day. But it is such a cool, there's so much here. It is insane. Very quickly, just to let you know, if you go home or just go to somewhere there's a computer, type into Google Fibonacci space anything. Anything. You will get hits. One of my friends, he's no longer with us, but he was a financial analyst. And during the recession in 2008, he was putting money in the stock market according to the Fibonacci sequence, and he was making money. It had to do with counting the number of times it dipped and went up. And I'm like, it's great for you, Sean. You have enough money to do that. You gotta have money to make money. It's very true. Fibonacci music, Fibonacci art. There's a huge connection between Fibonacci and art. Fibonacci music is big. Does anyone use an alarm to wake up in the morning? Is anyone willing to tell me what it sounds like? Or is it music, or is it like, does anyone have a Yes? Would you agree that that's, yeah?
Depends on how later.
Huh?
Depends on how later.
Oh, I understand. Okay. I understand. I don't use music because I started to incorporate the music into my dream, and I just kept sleeping. I'm like, well, that's not going to work. I need freaking that is because the frequencies that go into creating that sound are not elements of the Fibonacci sequence. They're not, their ratios are not multiples of the golden ratio. This is silly. So things that are pleasing to us, a combination of notes that are pleasing to us, are actually, their ratios are close to the golden ratio. Or some multiple of the golden ratio. You guys kind of with me? It's insane. And Jeff, you said you weren't going to, just look into it on your own time. Sorry. I could talk about Fibonacci all day, and I'll stop. You know, no, keep going. We can throw some sections out of 11 algebra. No, shut up. Okay, enough about Fibonacci. So Fibonacci, let's try to come up with an equation for it. Let's talk math. Oh shit, is anybody excited about it? So real quick, how did you get A3? How do we get A3? A1 plus A2, is that cool? How do I get A4? A2 plus A3. So how do I get AN? There you go. Now that is an unsatisfying function. Because if I want the 87th Fibonacci sequence element, that sucks. I can't just shove 87 in somewhere like we were doing before. This is what's called a recurrence relation. So every element is related to previous elements. Now there is a way, no Jeff, you promised me, blah, 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 it's enough of it. So I could have recurrence relationships. Some of them I could actually rewrite in a closed form, in like a function event. Some of them are much more difficult. Okay, how we doing so? I like it. Let me keep myself on track because to me, this stuff is fascinating, and I don't know if you're going to agree with me or not, but the amount of stuff we can do with what we're going to create in Chapter 11 is absolutely mind-boggling. It's insane. It is the first level of so many other processes. Has anyone ever heard of fast Fourier or like Fourier transforms? It's okay if you haven't. It's a very niche thing. But if you're interested at all in for example, we're not going to get into, I'm not going to, aliens. I'm not going to, but there's, you guys have all heard of SETI, Search for Extraterrestrial Intelligence. You ever seen the movie Contact with the very large array that's out there? You should go visit that place. It's kick's ass. So personally, I think it would be really almost impossible for us to be the only life that exists in the entire universe. That would be really arrogant, is what I think. So I think there is value in scanning the universe for signals. And how do we analyze those signals to tease out if they are natural in origin or potentially made by something purposeful? You guys kind of with me at all? Okay, I love it. I don't know if anybody out there's like, oh my God, is it going to get into ancient aliens? No. Okay. So Fourier transform is a way to analyze signals coming in and picking out the frequencies from the noise. Because there's going to be a ton of noise, especially if they're from far away, and the signal's going past who knows what kind of stars and shit. And a lot of noise comes in. So you should look that up. Look it up if you're all interested in that kind of thing. What we're doing in chapter 11 is going to kind of lead in that direction. For, depending on where you go after this class. Okay. So let's analyze this a little bit. How about here? How about this sequence here? Did I say recurrence? What the hell? Recursive. Recursive relation. Okay. Does anyone see what's happening here? Yes. Yes. So here I'm adding 2. Here I'm adding 3. Here I'm adding 4. Do you guys see that? So this is another example of a pattern within a pattern. I don't keep adding the same thing, but the amount that I add by is itself has a pattern to it. Okay. Now, let me show you something kind of cool. How do I say this? 1 plus 3 is 3 plus 6 is 6 plus 10 is
16.
anything. 10 plus 15 is anything interesting about those numbers?
Perfect squares.
They're perfect squares. Yes? You with me? All right, that's one little thing. Okay. That doesn't really help us get the equation down. But let me ask you this. What is you could do it, Jeff. What is how do I want to say this? Yeah, what is 1 times 1 plus 1 divided by 2?
1.
Yes, that's 1. What is 2 times 2 plus 1 divided by 2? 3. What is 3 times 3 plus 1 divided by 2? 6. 1, 3, 6, 1, 3, 6, yes? Let me stop for a minute. Is everybody with me? A little bit? So then what would AN here be? Notice the parts that keep changing, and the parts that stay the same, yes? So those parts stay the same. And of course, what am I going to put here? N. N. Okay. Now these are neat because if I do a visual of this, and this is what I probably should have done second, but too bad for me. If I do a visual of this, here's 1. Is that cool? If I take that 1 and I add a layer below it, that's 3. If I take those 3 and I add a layer below it, that's how much? 6. And I add a layer below it, that's 10. Yes? So you're not going to believe what we call these numbers. We call these numbers triangular numbers. And if you think about it, square numbers, now obviously we call them square because I square a number to get them, but to be honest, if I have 1 and then I have 4 and then I have 9, they all assemble into squares. Just like these assemble into triangles. So these are triangular numbers. And what's neat is you can see the square numbers coming from them. And those are square numbers. Okay, let me stop for a minute. Okay. Very trippy. Because all this is this plus this. And all this is this plus this. I know. All right, let me stop for a minute. Okay. So let me do this. I want to talk about 2 more ideas, and then I'm going to give you a little worksheet. So one level of sequences is teasing out the pattern you see. Sometimes I'm going to ask you to find AN, and sometimes I'm just going to ask you to describe the pattern because the AN would be really hard to get. Maybe that'll be a bonus. Yes, you guys kind of with me? Sometimes you're going to have a sequence that's recursive. Not recurrence, recursive. And a sequence that's recursive means you get one element based on what came before. There isn't a sequence, I just can't stop myself. There's a sequence called, you're not going to believe what we call this sequence. Does anyone see what's going on there? Here, I'll do one more. It's not Fibonacci, we call it Tribonacci because we are pathetically silly math people. Anybody see Tribonacci? T-R-I? Adding 3. And what we call these, by the way, like the 1, 1, 2 for Fibonacci, and these are called the seeds. Those are the things I must be given so the rest of my sequence can grow. So ready with me. What's interesting about Tribonacci is it has its own golden ratio. If you go far enough out in the sequence and start dividing elements, they're going to approach a number. It's like a limit. Oh shit. The thing with Fibonacci is it doesn't matter what 2 numbers you start with. You could pick any 2 numbers. Now you got to be careful. If you pick like -1 and 1, that's 0. What is it that I need to do? I can't remember. If you pick certain ones, this will be 1, this will be 1. Okay, that'll be fine. Fibonacci comes out. But if you pick certain numbers, you might just get nowhere. But almost independent of what you pick, the golden ratio still comes out. If you go far enough. Yeah, I know, it's crazy. So the golden ratio is something more fundamental. It's about the process, not the numbers. Is everybody kind of with me? A little bit. Okay. Sorry, I keep throwing these little things in. But these are so interesting. So, oh well, deal with it. What about this? Let me show you one way we represent sequences. One way is the way I already said, like we have this sequence like we saw earlier, yes? Another way is a little more explanatory. This one's kind of leading in the direction of something very important that we're going to get into in section 11 too. Do you see how the second one allows for more specific elements? Like, I have to assume when it's given to me like this, I must, does anyone know what the N stands for actually? Which will explain why we didn't start with A0. Natural numbers. And what do natural numbers start with? What came naturally to cavemen? 1, 2. What did we have to invent eventually? 0. And what does that look like? Looks like a whole. So whole numbers are just add 0 to natural numbers. Yes? So N literally stands for natural number. That's why we start with 1. So this, I'm going to assume it starts at 1. Over here, I can actually change this if I want to start later in the sequence. Is everybody with me? If I have it like this, it's understood to start at 1. Over there, I can specify what number I want to start at. Ooh. What else do I want to say about this? Oh. Very quickly, do you think this this sequence converges or diverges?
Diverges.
Yeah, and remember what that means. For an integral to converge, it's got to integrate to come out to be a finite number. And to be divergent, it just says to be not finite. It doesn't mean infinite, necessarily. For a sequence to converge, it just has to approach a finite number. And of course, what is this approaching?
Infinity.
Infinity. It's not approaching, it's just unbounded. Yes? What about this sequence? Obviously, this sequence will...
Converge to 0.
This sequence converges. Now, how do you show that mathematically?
Limit.
Yes. So here's another reason why I think you guys focus too much. Limits are coming back. Limits are big in chapter 11. And I think for some reason, I just figured that out, which is really dumb on my part. Students normally dislike limits. Is that true for anybody in here? Some of you guys right now are like, really? I thought they were, shit. Fine. Dear God, limits are so stupid important. They do things we couldn't do otherwise. They allow us to investigate things we couldn't otherwise. So here, to see if this converges or not, I just let n go to infinity. And of course here we're going to get 0, so that converges. Now the answer doesn't have to be 0. Does this sequence converge? We'll do that, yeah. Does anyone know what it converges to? Does everybody remember the shortcut from pre-calculus?
Yes.
Are the degrees the same on the top and bottom?
Yes.
Yes. So the limit as n goes infinity is just the ratio of the coefficients of the highest degree terms. Does that sound at all familiar? This is what you did when you found horizontal asymptotes. The horizontal asymptotes are just specific n behavior. Let n get really big, what's happening at the ends. Okay, maybe. So dear God, your old teachers before, did they have you divide by the highest power? Does that look familiar to anybody? Okay, screw that shit. Why would we do that? We've already gone through that shit. So if I give you a limit to infinity, and it's a rational function in n in this case, just get the answer. Don't go through all that crap. Why would you have to do that? So this would be 3 over 6, which is 1/2. Okay. That would be the limit. Let me be careful. The limit. Okay. So this obviously converges. Okay. Let me see. What else did I want to say? Nothing. Good. Let me do this. You want? Okay. So I put up on here some examples. There's your triangular numbers, pentagonal numbers, and again, you're not going to believe it, but you can put them in the form of pentagons. And then there's the Fibonacci numbers. There's the recurrence relationship. There's the seeds. Why do I keep saying recurrence? Recursive. What's recurrence in my head? I don't know. Okay. So can you guys just do these real quick for me? Notice what I'm asking. It might come back. So on one level, 11.1 and 11.2, if you let them, are a much breezier set of sections compared to chapter 7? You guys kind of with limits are coming back, but in very basic forms so far. You're plugging shit and getting numbers. You got just enjoy that while you can. Oh, gosh, I left you out there. Good work. Huh? It's been a while. All right, so here. Yeah. I'm sorry. I do that. I get into stuff and then I forget it. You missed some lecture, but we talked about sequences. Think of this sequence. That would be a 1, 2, 3. And then sometimes you can find formulas for like what 1 and the 11th term. They don't have to keep going. They can just put 11 in there. Okay. So all I'm asking for these is to figure out the first 4 terms, and they tell you where to start here. So just need to know the first 4 outputs, first 4 terms. Oh. Yes. So the first element of that sequence would have an n equal to 5. Yeah, that's it. That's it. Yeah, this is it. Totally. Yeah, so let that be nice. And then of course the limits are going to come back. Yep.
You start at
Third
8
power.
because they give you 8 of 1
Yeah. So if you try to plug in a 2 for n, it actually, you can't get an answer because you don't know what A0 is. So these are your seeds. They are the requisite information to have to get anything. So you can't calculate them, they have to be given to me. So what's the first value of n you would plug in for number 4? What's the first element you don't know? 3. I know a1 and 2. I don't know 3.
You wanna stop time?
I have a question about the calculator.
Yeah.
Does it square negative 1/2 difference compared to the square of negative 0.5?
No.
It's giving a different answer. Oh, cube. Never mind.
Oh, it's cute.
So it's 0. You start with 0. So this is 0. That one's 2. No, that one's 1. That one's 2. And this one's 2.
I was
So
like,
n is 0.
Yeah.
So for this one, you're plugging in 2. You're not 2. You're squaring. So that's your last term. So you're missing the
Okay, I think we did this. We did that.
Oh.
Okay. Okay, thank you. I think I was just missing that
Anything to the 0 power, so you do. Oh. Oh, zeros? So this, the first power, this to the first power, there should be. So there should be 0, 2,
that's the
1/2.
trick to be careful about it.
Oh,
You just put a 3 in
But
there,
it
but
is
no
zero?
a2
Even if
there,
the
so
negative is like in
that
parentheses.
would be 3 minus 2, 1,
Like,
and you
why
want
did
to
you
do
use
there.
parentheses?
See, if I put a 3 everywhere there's an n, let's do that first.
Yeah, yeah. Okay, the negative is like,
Then I'll know exactly where to put.
So it was right the same, right the first time.
And then for the third one, right here. It was in the third one. The third one is n equals 3. And you're doing n equals 2.
Because, yeah, because this is a 2, and this is a.
You're missing the third term, which is n equals 2.
Oh, so, right to yourself, just do this. So that's 2a2 minus 3a1.
Wow, that's really interesting.
Oh, I see.
Yeah, and then you just, yep. So people try to skip steps and it gets all jumbled. I don't know, where's your one? So, it'll be,
Oh, this is supposed to be a 2.
10 minus 6 is 4, sounds good. And then it'll be, 8 minus 15? Yeah, okay.
What?
Good.
Oh yeah, my 5 is
Yeah,
it is.
first portion. 0, 3, good. Yes, good.
I just wasn't doing it in parentheses properly.
That's what I read in the calculator.
You already gave it the first 2. So you really
Well, I
only
didn't
need 2.
really
But if you
care
do
this time.
6, I don't care. I did more work.
Me too.
Okay.
Thank you.
So to me, we just barely scratched the surface here, but I mean, this really opens up a lot of really neat avenues. Obviously, all of mathematics is basically can be boiled down to finding patterns and building processes off of those patterns. This is just frickin' patterns in your face. This is just, that's what it's all about, is the pattern. And oh my God, there's so much shit you could do with this. So this is easy. We basically already did this one, yes?
Yeah.
So 1, 1/2, 1/3, 1/4. What could you do? This one, start at 5, so the first term would be 5, 6, and it's just the bottom is always one more than the top, right? So you don't actually have to plug shit in. You just have to keep going up by 1 each time. How's that? This one, I heard a lot of interesting things. So 0 is easy. 1 plus 1 is 2. That's crazy. And then when I plug a 1 in, it's 1 minus 1/2. Is that cool? So every odd power is going to go down. Every even power is going to go up. So it's going to be oscillatory in nature. 1 minus 1/2 is incredibly enough. 1/2 is crazy. And then 1 plus 1/4. 5/4. And then 1 minus 1/8. 7/8. So this one, do I come back to that one? No, because I'm a dork. What would the limit of this be?
1.
Yes, you're approaching 1 from both sides. So it's cosine and sine are the most in-your-face periodic functions, and if I dampen them like plucking a guitar string, they oscillate around a central, the midline. Yes. This kind of mimics that, but just not continuous because this is obviously discrete, the one that's off the page now. But it does oscillate around the midline of 1 forever, just eternally getting closer. So what is the limit of this sequence? 1. So does it converge? Yes. So that is it. For a sequence to converge, the limit just has to be a finite number. That's it. So does that mean every sequence that does not converge goes to some kind of infinity? No, because we'll get there. We'll get there. We're not talking about that yet, Jeff. Now, on this problem, all right, it's not impossible to do this in your head, but it's a little silly because you can start putting stuff in the wrong place really easily. So if you just literally write for yourself A3, everywhere I see an n, I'm going to put 3, so 3 minus 1 is 2. 3 minus 2 is 1, and now I know exactly where to shove A2, and I know exactly where to shove A1. So then A3 is 10 minus 6 is 4. A4 will be twice A3 minus 3 A2, and now I know A3, and I know A2. So I get 8 minus 15, negative 7. How's that? Sorry, it's off the page. So sequence element generation, dear God, Jeff, give me a bunch of that shit, because it's just plug and chug. So obviously I'm not going to give you a bunch of that, because who cares? You will get a little bit of that. The more interesting thing is, if I give you elements, can you come up with an on your own? Okay. We'll get some practice with that later. Limits. I kind of reminded you guys about this silly thing, but now I've shown you, why did I do it this way? Just the shortcut, yes? Screw this, screw this. They have both second degree, so it's 4/3. Kabam, yes? And we know L'Hopital's frickin' rule, yes? Now, does anyone see what I had to be careful about if I wanted to use L'Hopital's rule? Because what is L'Hopital's rule fundamentally built off of?
It has to be 0, 0.
Okay, good. I like it. So when does L'Hopital's rule work? If it's in an indeterminate form that can be written as a ratio. Yes? So ready with me? So it works on more indeterminate forms than that, but it needs to be rewritten in a ratio form. But what do I use to do it? What is it built on? Not when does it work? I appreciate that, but what is it built on? Derivatives. Yes? It's all about which one's getting to where it's going quicker, which is intuitively a kick-ass, simple idea. Before I teach L'Hopital's, I try to use that language as we investigate why limits are what they are. Well, which one got to where it was going faster? That's what this is. And then that it just naturally leads to derivatives, because that derivatives are rate of change. Which one's going and where they're going faster. So if I do L'Hopital's on this, I can't use what I'm given. Why not? Why are sequential functions not differentiable? If I graph a sequential function, what would it look like? It would look like dots, yes? You with me? My inputs are values of n, and my outputs are distinct numbers. So if I graph this, it'll have n is 1 and have 1, n is 2, 1/2, n is 3, 1/3. Derivatives are all about what your function is doing. Immediately, instantaneous rate of change. But what is my sequential function doing? It's here, and then it teleports over there. It's like, what's the derivative if they're not even connected? There's no path. I could go this way. I could go straight. I could go down. I do none of that. I jump. So derivatives are like, I don't know. But the beautiful thing is, I can model a sequence using real valued functions. So that's what we do. If I replace my n's with x's, these limits are the same. Just because I fill in between the dots doesn't change where the dots are going. Does everybody understand what I just said? But if I fill it in, now I could do derivatives. because now I can see there is a next place it's going immediately. There's an instantaneous rate of change. This is a point right next to the point I'm at. And a lot of you guys are going to skip this step, but I need you to understand why this step is important. I know it would look the same if you just did L'Hopital's here, but it would be wrong, which is important. Okay, maybe. So you still get the same limit, of course. Okay. So I wouldn't use L'Hopital's in this dumb thing because it's just polynomials. Who gives a shit? I would use L'Hopital's if it was like trig functions and who knows. Okay. So give these three a try here. These three right here. Shwa. And no, you don't have to use squeeze theorem in part B. We're past that. I always thought it was silly we did squeeze theorem in part B in 180 anyway. Oh, that's right. Didn't bring that. Yeah, okay, that's perfect. I love it. Okay, let's see. First guy. Converge or diverge? Why?
Bombs growing faster than the top.
Bounds growing. Okay, sorry. That was me. I need more of whatever this is, or less. Let's see. I can't tell yet. The bottom is higher degree. What will the limit be? Which is a different question than what I asked, I know. The limit would obviously be 0. I like Macy, out of the corner of my eye, it's like, what is she doing? Oh, she's answering the question. This one, does anyone know what this does? When n gets really big, what does this do? True. Be more specific. It approaches 0. And what does this do? Forever. Goes between 1 and -1. So if I put a number out here, what would that be according to the trig function? If I had a 4 out there, that would be that trig function's. Does anyone know? If I put a 4 in front of the sign, what would that do? That would make the sign go between. You can do it. Sine by itself goes from -1 to 1. If I did 4 times sine, it would go from -4 to 4. So that's the amplitude, yes? So I have a non-constant amplitude. You guys with me? If my amplitude was 1/2, then that would be, right? The amplitude is 20. Whoa, yes? What is my amplitude doing as I let n get bigger? My amplitude is getting smaller, going to 0, right? So even though sine oscillates forever, the limit as n goes to infinity of sine is not finite and it's not infinite. It's oscillatory divergence, yes? Mm-hmm. That sequence would diverge. The sequence sine n would diverge. But this sequence, in fact here, I kind of altered it just a bit so you can see it better. But that's basically what it would look like if you zoomed in. This is plucking a guitar string, dampened oscillation, dampened harmonic motion. Thank the gods, or else every guitar ever plucked would still be going. And we'd all like, how you doing? Oh my God, okay. So that's dampened oscillation. This is going to go to 0. That's exactly what's happening here. And some of you guys, I don't know if you remember squeeze theorem. I said squeeze theorem earlier. Do you guys remember squeeze theorem? Or have you put it out of your memory? So this is 0 times finite, which will always be 0. Only 0 times infinite would be indeterminate form. Because then it would depend on who's getting there faster. Yes? Okay, maybe. Yes, with me. That's why I always hated that we made a big deal out of this. Of course the damn answer is 0. 0 times finite. It's always going to be 0. Okay, maybe. What do you do on part C? Oh, did anyone do anything on part C? What do you do? What do you do when you have no idea? What do you do just to get a feel for what might be happening?
Start plugging in numbers.
Yeah, just plug in like 99, 909, just plug that shit in the calculator. Just to give yourself an idea about what it looks like it's doing. You never know, that might spur something, you might think of something else to do. Just to see what the shit this guy's doing. Yes? I can't do the same thing we did on part A because the top is not polynomial. In fact, if it was at least a power function, a series of power functions, you could still do it. But it isn't. It's a natural log. And we talked about natural log before in here about how slowly it grows. But what should I do to investigate this then? To get an answer instead of just a estimate? Well, all right. What happens to the top by itself? Goes to infinity. What happens to the bottom by itself? So, what person that feels like they're working in the medical field could help us? L'Hopital, because that's ratio. That's an indeterminate form. Yes? Yeah, I like it. But what do I have to do officially before I do L'Hopitals?
X.
Convert this to X stuff. And I'm gonna, at the same time, I'm gonna write that in a better form for a derivative. So this is the limit as x goes to infinity. What's the derivative at the top? 2x over. And what's the derivative at the bottom? 1/3. Okay, so let me give myself some more room. Let me rewrite what we got so far. Jeff, my God, dude. 2x over x squared plus 1 over 1/3 x to the 2/3. This should be our bread and butter. Is it negative? Oh yeah, that's right. So, how do I do this? Well, one thing I could do for myself, and of course there's a limit in the background here, but I'm not going to keep writing. This is divided by 1 over, you could do it, Jeff, by 1/3 x to the negative 2. We'll just do that. Okay. Which is 2x over, I'm going to overdo this just because, divided by 1 over 3 x to the 2/3. Is that cool? Which, again, is 2x over x squared plus 1 times 3x to the 2/3. And there's still a limit, blah, blah, blah. One semester, I told my students they could just make a big L to replace that, and they could always reference back to what the limit actually was going to, just to make it quicker to write this shit. So that becomes 6x to the 5/3 over x squared plus 1. And now I can see which degree is higher. The bottom is, yes? You with me? 5/3 is smaller than 2. So what's this limit going to be? 0. Because the bottom's got a higher degree, the bottom's growing faster, the whole thing's going to get small. Okay. How we doing? So let me see if is everybody semi-cool with this? And this is where a lot of students at this level sort of like just freak out and do all kinds of neat things. If you're just more careful with it, if you don't know how to go from here straight to there, yeah.
If the degree is higher on top and the bottom, it goes to infinity.
Infinity. If they're the same degree, they go to a finite number. Between 0 and infinity, yeah. Unless there's a negative number. Okay. Now, let me point something out. Does anyone notice what that means effectively? This thing went to, you already forgot what the hell you just said? 0. This thing went to 0. And it only goes to 0 if the bottom degree is higher than the top. So effectively this means the natural log sort of acts like a polynomial with a degree smaller than 1/3 at least. Now some of you guys might notice, I could have made this the 11th degree. And the same thing would happen. I could have made this blah, blah, blah. So somehow natural log has a lower degree than any n to any pair, which is neat. Yes?
That's what I was gonna ask. Would you count it as growth? Because in pre-calc they showed us like, oh, this is how fast it grows. So whenever there's a natural log, I just assumed it would grow.
Oh, okay, sure. Yeah, if you guys kind of proved.
Guessed it was gonna be 0 because natural log like grows really, really slow, and the other one would grow.
Yeah, natural log grows slower than any power, which is crazy. Okay. Crazy. This is a good thing to know. Yeah, you're right. Okay, but be careful. There could be other stuff
Yeah,
happening.
the thing that confused me is there's an n square inside.
Sure.
So I didn't know if that was gonna.
So you
change
do have to be
something.
careful. I could potentially put funkier functions inside that could have certain effects. So you don't want to necessarily jump to the answer, but yeah, jump to it like that. Okay. How are we doing so far? Is everybody okay? So limits have come back, but they're not new. Creating elements of a given sequence are easy. Just plug in values in for n. I think the hardest thing we're going to have to do in section 11.1 is this last grouping. Potentially the hardest. Can you guys try the first 2 of these out? If you haven't tried these out yet. This one is easy as shit. So what I really mean is just try the first one. I mean, B we already did. The first one shouldn't be too bad. So just don't forget, this is A1, which means n is 1 here. This is A2, which means n is 2 here. Yes? So you just have to capture how each element is changing based on where it is. So what's always true, that the top is how related to its position.
It's n.
Yeah, the top is the same as its position, so the top is going to be n. And the bottom is always
One bigger.
one more than the top. Done. That's something to realize, by the way. If you have fractions in a sequence and you can see a relationship between the top and the bottom, that kicks ass. Because now if you just figure out what the top is and you see the bottom is always 2 less, you just write top expression minus 2. It's not like, yeah, okay, maybe you can see that. This one is easy. This one we already did. Blah, blah, blah. What about this one here?
3 minus 2.
Yeah, now here's the shortcut for this, because we did it kind of longer way earlier. I know the slope is 3. Because every one step it goes up by 3. So I'm going to write 3n, and I'm wrong, because when I plug a 1 in, I get 3, not 1, so I just got to take 2 off. So it's just, they're just multiples of 3. They're off by 2 from multiples of 3. That's another way to look at that. Instead of 3, 6, 9, it's 3 minus 2, 6 minus 2, 9 minus 2. Okay, maybe. So this is an arithmetic sequence, meaning I'm adding, subtracting the same thing. Yes?
Could you just do like an minus 1 plus 3?
Oh, if you wanted to write this recursively, is that what you're saying?
Yeah.
So like, what would an be? It would be an minus 1 plus 3, yes? Now, this is always less satisfactory than this. But sometimes this might be the only way we could see how to write something.
If I were to write that, it would be
It would be wrong. I always want a, like, I don't want to call this, non-recursive form, if it's possible to get. Well, let me say it better. I will tell you when to rewrite something recursively. Yes, let's just say that. By the way, I mean, this is a great, you could write every sequence recursively. Because inherently, they do have what you do to the other one to get to where you are. What about this one? What's different on part D? It's basically part B, except what?
Alternate signs.
It's alternating signs. In fact, you're not going to believe what math people call this. We call it an alternating sequence. Yeah, I know. We were like, what should we call it? It took us a few days. You know what? How do I capture that mathematically?
Negative 1 to the n minus 1 power.
Yeah, so it's all about, I'm going to multiply by negative 1 to a power, and I just have to, there's literally an infinite number of ways to write this, but you try to write it with the smallest amount of stuff you can. So it's going to be 1 over n. That's at the heart of it, yes? Mm-hmm. But it's negative 1 to some power. And if I just do this, is that right?
No.
Because when I throw a 1 in, the first element should be negative, and it isn't. So then I just either do minus 1 or plus 1. It's up to you. I could even do plus 3. I could do plus 11. But we just use the smallest thing necessary. Okay, does everybody see that? Whenever you see the signs change from you're going to have a negative 1 to the n, or a negative 1 to the n plus 1, or n minus 1. It's up to you. That's the alternating sequence piece that makes it do that. Okay. Yes.
I was thinking of, is it right if we put that on top of the fraction? Would it still be the same?
Do it again, sorry.
Put it together, so like.
Oh, yeah, sure. You could write this like this.
-1.
That's fine. I kind of like to write this by itself, and later this semester you'll see why. There'll be times when we take absolute values of these things, and if I have that dependence written by itself, I see what's left over. Can anyone tell me what would the absolute value of a and b? You could do it. You could do it. Every negative element becomes positive, and every positive element stays positive. So what's an? Absolute value of an. 1 over n. Absolute value of an would just be this business. That is the absolute value of this. Do you guys see that?
Yes.
So just, you were right, just, I always like to put this by itself, so I can always capture this if I need to. Absolute value, easy. Oh, let's not talk about that yet. The back of the sheet gets nifty. Let me ask you a question here. How many guys know what this means? Is that 5? Sorry. What is 5 factorial, and what does that mean? It's not based on addition.
Multiplication.
It's multiplication. Yes?
Squared plus 5 cubed.
No squares or cubes. Nope. It's literally 5 times 4 times 3 times 2 all the way down to 1. So 87 factorial would suck to do by hand. Yes. What would this be though? What would this be? What's 87 factorial?
86.
87 times 86 times 85 times 84, and then this would keep going to 1. How do I write 84 times everything down to 1? Like that. Do you guys see that? I would take 87 and go all the way down to 1, but at any time I want to, I can stop and just put an exclamation, which just means keep going. And of course, why do I want to stop there? Because now I see those dumb things go away. So what is this?
N plus 2 times n. I keep calling it bangs.
What do you call it?
Bangs because of computer science.
Oh, okay.
Exclamation points.
Oh, you call them bang? Really? I had no idea.
Yeah.
Got to trim those bangs. Now watch. What is the idea of factorial? What does it do? It keeps doing what? How does it get the next thing it's going to multiply by? What do you do? How do you get the next number? Now, what was 7 factorial again? 7 times 6 times. How does it keep figuring out what the next thing to multiply by is? Subtract 1. So it's very single-minded. Yes?
Yes.
So 7 factorial starts at 7, then it multiplies by 7 minus 1, which is 6. All right, and that's what a factorial always does. It can never do something different. That's what it does. So what is n plus 2 factorial? N plus 2, just like 7, it starts off where it is. N plus 1.
And factorial.
I wouldn't want to stop at n. What's after this? Do I want to stop there now?
Yes.
Of course I do, because now these dumb things cancel. Yes, the same thing, just looks worse. Because it's got n's instead of numbers, yes? But do you see how n plus 2 is just a number? I just don't know what it is yet, because nobody told me what n was. So it has to act just the same way as numbers do, because it is a stupid number. That's the whole heart of math. X plus 3 is a number. It has to act like any other number does, because it's a number. Okay. Why am I spending so much time on this? You're going to see a ton of this shit. You're going to do exactly what I just did, and even more interesting shit. Blah, blah, blah. Oh, how would I determine, what do you guys think about this? What if I gave you a sequence? What do you got, Jeff? I don't know, Jeff. And I said, is this increasing or decreasing? So what I want you to realize, this is huge. This will be the last thing I talk about. I'll let you guys out of here. This is huge, what I'm about to say. Okay. When I say something like, is this an increasing function, sequence generator? Is this an increasing function of n or not? it could be decreasing for a little bit and then start to increase forever. What matters is, what does it do forever? So if I ignore the first couple elements, do you guys understand? I don't know if I can do it on the spot, but I have developed functions in the past where if you plug in n equals 1, n equals 2, n equals 3, it's going down. But if you just went to n equals 50, n equals 51, it suddenly starts to go up now. So if you do the first few elements and you go, well, this function's decreasing, Jeff. I'm like, no, it ain't. So I have to have a way to do this that does not depend on me plugging in enough numbers to see what the whole thing is doing. There must be a way to do this without that. You guys got it with me? I don't blame you. In fact, you don't make any sense to me if you don't plug some numbers in just to get a feel for what it's sort of doing, but you can't make any generalizations based on that. So does anyone know how to see if this is increasing or decreasing? How did we do it in Math 180? Derivative. So what do I have to do, of course, before I can take a derivative?
X.
Yes. So then if I take this guy's derivative, help me out. Everybody's favorite. Do you know the song for this? Where are my students at? Do you guys remember the song for this? Sorry, they're looking at me like, whatever, math boy. You thought it was funny. Here's the song. You ready? Here's the song. Top first. Sorry, I mean, top first. So, high-low bullshit. Bullshit. I always hated that because it rhymes two different ways, so screw it. This is just, real quick, guys. Derivative of the top first. Why is there a minus here? Why does that minus make nothing but sense? What am I about to take the derivative of? The thing that's on the bottom. If I brought it up, what power would it have? Negative 1 power. So of course it's negative when I'm about to take the derivative of the thing that's on the bottom. So I'm really sorry. I have this it's too bad. Some of you guys know the Heidi-Lo, blah, 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 blah. It's just so much bullshit. It's better to understand why it is the way it is instead of some song taking the place of understanding. I have nothing against music, but we bring it in too often. So now I leave the top alone. Derivative of the bottom is easy. All over this squared. So I get 2x squared minus x squared is x squared. That's crazy. And then I get 4x minus negative 4, so plus 4. Ooh, this is neat. I didn't even mean to do this. Holy shit. Is that true?
Yep.
Neat. So this becomes
1 over x plus 2.
1 over x plus 2. Now, can anyone tell me, for values of x 1 and above, because that's what this is assumed to do, yes? Is this positive or negative? It's always positive, right? So depending on your results, you might have to kind of work it out. I'll do some more examples of this obviously next time, but if I replace my n's with x's, I'm now able to analyze it using derivatives. And of course, if the question is increasing, decreasing, that's what derivatives are all about. This is always positive for x values 1 and above, correct?
Yes.
And of course, from the beginning, the assumption is the lowest input is 1. So this is always true, so this is always increasing. For the example I gave before, if you do this work, you'll be able to actually figure out when does it go from negative to positive. You'll know exactly when it starts to increase. You guys with me still? Mm-hmm. And that's going to be huge for what we're going to get into in section 11.2. And just a little preview. 11.2 is called, investigate something called series. And all a series is if I take a sequence and I add up all the elements. Now on the surface, that feels like if I have a sequence like this, what do I get if I add up all the elements?
Infinity.
Yeah. Does every sequence add to infinity? Hell no. Now, on this, have I already said this to you guys? I feel like I did. But maybe it's just because I taught 280 a lot. I'm sorry. this is such a cool idea, because normally people kind of balk at this. Could I add up an infinite number of numbers and come out to something that's not infinite?
Yes.
The easiest example of this, part of me loves that everybody's cool with that, and part of me hates that. I always want somebody to go, of course you can't. What do I get when I add these up? Does everybody agree there's an infinite number of these? Couldn't I just keep adding zeros? Basically, I'm dividing by 10. That's the definition of this sequence. Just keep dividing by 10. What does it add up to be? Do it again. 1, 1, 1, 1, 1, 1, 1, 1, 1. Yes? Does anyone know what that is as a fraction?
1/9.
1/9. Because what's 0.333 forever?
1/3.
Or 3/9, yes? So 0.3 forever is 3/9, so 0.1 forever is 1/9. 0.2 forever is 2/9. Everybody with me? So that's an infinite number of numbers that adds up to be something smaller than 1, which is neat. So obviously, I'm going to have some series, which again is just sums of a given sequence. I just have a given sequence. If I add up all the sequence elements, I call that a series. So a sequence would be 1, 1/2, 1/3. A series would be 1 plus 1/2 plus 1/3. It's harder for a series to converge than for a sequence to converge. Does that make sense? Because a sequence, the individual elements just have to go to something. A series, I'm adding them all up. Holy shit. Okay, maybe. Okay. I think this is good. We'll stop there. Tomorrow, listen to me. Thursday, I have a handout that I'm going to have you guys start off with that summarizes some of the stuff we just did, like factorials and stuff. And then we'll get deeper into series. Okay. Did everybody get their test back? Anybody come in after? Oh. Anybody else need their test? Who else needed their test back? Who else needed their test back? Oh, yeah.
Oh, professor. Isn't the x squared plus 4x plus 4 over x squared plus 2 just 1? He just
Do it again.
Just mentioned it right now. You're the one who said it. I was the one who said it, yeah. I was the one who was wrong. That's why I was like hella confused. Like, how the hell did that become 1 over x plus 2?
Do it again. Sorry. Wait a minute. Oh, here it is. Oh, yeah. This should just be 1, which of course is always positive. Yeah.
Yeah, so like I was really confused.
Well, because I saw 1 here. I didn't factor in my head.
Okay.
I went too quickly.
Yeah.
But yeah, it should just be 1, which still is always positive.
I just started questioning my life. No, you were right.
I need to remind everybody, I'm just a human. I make mistakes all the
And I was the
time.
one who told you. I was the one who was like, doesn't it factor? I was like, yeah, it does. So I reinforced you.
Oh, no. I was surprised it turned into something, especially because it made it up out of nowhere.
That's what
I was like, ooh, this factor's nice.
That's what I thought. Like,
Yeah.
one factor's nice. And I just
Yeah.
got one factor. Number one.
Sometimes I just want to do it wrong for some
You
reason.
were right. It is just one.
It's just 1, yeah. Which still is positive. Yeah. I think I was upset. I wanted it to turn out to be something dependent on x. Because then that makes it a more general problem. If it just comes out to be a number, you just look at it and go, it's positive, okay. But if it's dependent on x, it could have specific places where it's increasing. Yeah. Okay.
So because the derivative is positive, does this mean that the series